In today's lesson, we're going to be looking at the next section of continuity now that we've dealt with limits, and this is called continuity. Continuity in terms of the regular functions that you sketch in core maths doesn't really come to discussion because it's normally just one type of graph and you don't have what we call holes in the graph. But we're going to look at now what happens when a graph is continuous at a point or when it's discontinuous at a point. And when it's discontinuous at a point, in other words, there's a hole in the graph, we have two different types of continuities. One is a removable discontinuity, and the other is a jump discontinuity. The way this lesson will work is it's going to be split into three parts. Part A is the definition of continuity. Part B will be removable discontinuities, and Part C are jump discontinuities. Now, on the year plan, or at least on the schedule for this section of calculus, I've given you to complete Part A between the 25th and the 27th of May. Then Part B should be completed between the 28th and 29th of May. And then Part C, the jump discontinuities, from the 1st to the 3rd of June. The video is just going to be one long video. So, in other words, I would suggest that you spend the first few days just going through the video, look how long the video is, and break it up where you feel you need to stop, and spend even until the 29th of May just going through the videos, making notes, etc. And then after the 29th of May, you can work through the exercise, which is fairly lengthy in the textbook. But I'd rather do the whole of continuity together so that because it all links to each other and questions involve both types of discontinuities, etc. So let's start with the definition of what continuity is. Right, if you look at the graph in front of you, I've drawn any random graph. It looks more like an exponential graph than anything, but the type of graph is not important. And we're going to discuss the continuity of this function. Now, when you talk about the continuity of a graph, you're actually talking about at a particular x value, is this graph continuous or is it not continuous? Now, the easy definition of continuity is that if we look at where x is a, so the x value a is at that point on the graph, and if we had to work out the y value, we'd substitute it into the function f of a. But at that point, is the graph continuous or not? Now, what that means is, can you, from the left of the graph, travel along the graph through that point without picking your pen up off the paper? And here we can see clearly the graph is continuous, all right, because it continues through that point. Let's look at a more formal definition. We say that a function is continuous at x equals a. Remember, a represents any point on the graph, if and only if. So this expression is important, if and only if, meaning that these conditions have to be satisfied in full in order for a graph to be continuous at that particular point x equals a. So this is the definition. The limit as x approaches a from the negative side must be equal to the limit as x approaches a from the positive side. So that in itself, what I'm circling in blue here, or squaring, is the normal condition for a limit to exist. Okay, the fact that the limit from the left and the right equals the same value means that the limit exists. But in order for the graph to be continuous at that point, it also needs to be equal to f of that value. In other words, the y value, when x is that particular a value, must be equal to the limit. So in example, you'd get the limit from the left equals 3, the limit from the right equals 3. That means the limit exists at x equals 3. But if we substitute that a value into the original function and we get y equals 3, then we would say that the graph is continuous. Let's look at an example. Right, so example 1, prove that f of x equals x squared is continuous at x equals 3. Now, you don't need the graph for it, but let's just sketch it to get an idea of what we're looking at. Okay, so there's the parabola. We're now looking at this point when x equals 3. Is the graph continuous at that point? Right, so the first thing is look at the definition. We need to determine what the limit is of this function, whether there is a limit or not. So let's first look. The limit as x approaches 3 from the negative side of x squared, we can substitute the 3 straight away to get a limit of 9. Now we're going to look at the limit as x approaches 3 from the positive side of x squared. And you'll see we get the same answer. All right, so this now means that the limit exists, okay? Because the limit as x approaches 3 from the negative side of the function f of x equals the limit as x approaches 3 from the positive side of f of x, we can say, therefore, the limit exists at x equals 3. All right, so all we've really proved now is that the limit exists at x equals 3. The last thing we have to do is now say, if we substitute, we've got our equation, f of x equals x squared. If we now substitute that x value, and we get the same value as what our limit is, we can then conclude that the graph is continuous at x equals 3. All right, so we're going to just conclude by saying, therefore, f of x, or just f, we can say, is continuous at x equals 3. All right, so remember, why is that? Because the limit from the left equaled 9, the limit from the right equaled 9, and when we substitute the value of x into the function, we also equal 9. So those three values all have to be the same in order for the graph to be continuous. Right, so what that example taught you is when a graph is continuous. Now we're going to look at part B, which is called removable discontinuities. And I'm going to teach you how to determine whether a graph has a removable discontinuity. Right, if you look at this definition here, or this example, I've got a general function f of x. And we could say, let's call this example 2. We can say that definitely the limit from the left and from the right both equal 3. Right, so we can't actually do working out here because we don't have the function, so we don't have anything to substitute in, but we can see from the diagram that as x values are approaching 2 from the left, the y values are approaching 3, and as they're approaching 2 from the right, the y values are also approaching 3, which means that the limit is equal to 3. But we can also see that f of 2 in this function, if we had to substitute into f of x, we'd say that f of 2 is undefined because there's a hole in the graph. That means that there is a removable discontinuity at x equals 2. Right, so a removable discontinuity is when the limit exists, but there's a hole in the graph. All right, an open dot that represents an undefined value at that particular straight line. So let's summarize quickly. Removable discontinuity, we would say the following two definitions have to be applied. All right, first, the limit exists, or the limit must exist. That means it's the same from the left and the right. And secondly, f of the function is undefined at that particular x value, whatever we're looking at. Remember, if I'd taken x equals 1, in this particular example, it would be defined and there would be continuity at that point because there are no holes in the graph at x equals 1. But at this particular point, x equals 2, the limit exists, but f of 2 is undefined, therefore there is a removable discontinuity. Okay, if we look at example 3, and I ask you determine if the graph is continuous, so let's say, is the graph, or is f continuous at x equals -1. All right, now by virtue of the fact that there's an open hole at x equals -1 on the graph, we can already see that it's not continuous. We've now got to prove what type of discontinuity it is. Okay, so again, we start with working out the limits. So we're going to say that the limit as x approaches -1, we can see of f of x is equal to 3. Okay, as x approaches -1, from the left-hand side, sorry, I should have added that in, from the left-hand side, from the negative side, we can see that as x approaches -1, down this graph, the y value is approaching 3. Similarly, we can say that as the limit approaches x as x approaches -1 from the positive side, the limit is also 3. Okay, so the fact that the limit approaches 3 from the left and the right means that the limit exists, but now, which means that there is a discontinuity in this graph, because we're going to now say, but f of -1, when you substitute -1 into the function, we get this coordinate there, that where the y value is 4. All right, so because of the fact that the y value is equal to 4, and now this value is different to the two limits of equal to 3, we would say that because the limit exists, but because f of -1 is not equal to what the limit is, we would then say that at x equals 1, or -1, there is a removable discontinuity. And please ignore my spelling. It should be removable discontinuity. Okay, so just to go back and clarify something, I cannot draw this line past that open dot without lifting my pen. That's what makes it discontinuous. What makes it continuous is that on the immediate other side of that hole, the graph was still approaching from both sides the y value of 3. So that makes it a removable discontinuity, because the actual value of -1 is undefined at that point, but it is defined at f of x at y is equal to 4. All right, so it's not just a removable discontinuity if f of the number is undefined, but if it's a different value to whatever the limit is. The last part of continuity or discontinuity that we're looking at is known as a jump discontinuity. And the name of it almost implies exactly what it does. So it's discontinuous, but the graph jumps. And I'll explain now what that means. So the definition: if the limit as x approaches a does not exist, in other words, from the left approaching a and from the right approaching a are two different values, and the limit doesn't exist, then we say that the graph, or f, has a jump discontinuity at x equals a. Example 4, discuss the continuity at x equals 2. Right, so firstly, again, this is a generic function, so we're not going to actually be doing any substitution, but we're going to look at the information that's given on the graph. So firstly, they've said, now look at the wording of the question, discuss the continuity. So they haven't said whether it's continuous, whether it's not continuous, and if it's not continuous, is it a removable discontinuity or a jump discontinuity? All right, so we first got to establish if in fact the graph is continuous at that point. And although we can see from the graph it's not continuous, we have to show using calculations. Right, so firstly, we're going to investigate the limit from the left and the right. Right, so firstly, the limit as x approaches 2 from the negative side of f of x. So now we're looking as x approaches 2 from the negative side, we would say, and at this point where my pointer is, the x value now equals 2, so the limit then is -1. Right, now if we look at the limit as x approaches 2 from the positive side of f of x, then we can see that the limit approaches 1. As the x values from the positive side approach x equals 2, the limit equals 1. Right, so by virtue of the fact that these two limits are not equal, we can at this point state, therefore, f is discontinuous at x equals 2. So we've established that it's discontinuous. We don't have to go further now and say what is f of 2, because that doesn't matter. The limits are unequal. Okay, but having said that, let me show you that f of 2 at least is equal to 1, because when the x value is 2, the y value is 1. That's where we've got the solid dot on the graph. But because the limits are not equal, we would say that at this point we can conclude that there is a discontinuity. It's a jump discontinuity. So f has a jump discontinuity at x equals 2. Okay, so remember, why is it jump? Because the limit from the left and the right are not equal. And let's see why the word jump comes in. Because as we trace the graph from the left to the right, we get to the point where x equals 2, and then we have to jump over open space to get to the continuation of the graph at x equals 2, and then continue. Okay, just one thing I'd like to point out to you. If the graph was actually open dot as well at the point where x equals 2 and y equals 1, in other words, it looked like this. If it was an open dot, it wouldn't change anything. There's still a jump discontinuity at that point, which is why it wasn't expressly important to show that step once we know that the limits are unequal. Example 5, discuss the continuity at x equals 0, and again we're going to call this function f of x. So we would say that the limit, and remember f of x includes this part and that part because they haven't been labeled separately, so we assume that they're part of the same composite function. Right, so the limit as x approaches 0 from the negative side of f of x, look at the diagram. So as x is approaching 0 from the negative side, the y values are approaching infinity. So the limit as x approaches 0 from the negative side is infinity. And the limit as x approaches 0 from the positive side of f of x, again look at the diagram, as the x values are approaching 0 from the positive side, the y values are approaching -4. Right, so again, the limits do not equal each other from the left and the right, so we can at this point say that the graph is discontinuous at x equals at x equals 0. So and because the limits are not equal, the type of discontinuity is a jump discontinuity. Right, so therefore there is a jump discontinuity at x equals 0. Alright, I hope this is making sense to you. And let's have a look again why it's a jump, because as we move from the left to the right, this is going to go on to positive infinity. We're never going to get to 0. But in order to get to the next part of the graph, we would have to jump down to the -4 on the y-axis and then continue on the function itself. Alright, so there is the jump, the gap between the two different parts of the function. Okay, so the first 5 examples were just to kind of introduce you to the theory of discontinuity and continuity. From now, we're going to look at the next few examples, examples 6, 7, and 8, when you're actually given functions to analyze. Right, so let's have a look at this one. It's a composite function. F of x is equal to x plus 3, that's this one, if x is less than or equal to -1. So there's the less than or equal. Okay, that's where the function can be equal to -1 on the x-axis. Then the absolute of x, if x is between -1 and 1, not including. And then lastly, x equals 1 if y equals 1, or f of x equals 1 if x is greater than 1. That's this portion. Right, the question is in 3 parts. First, state the values of x for which the function f of x is discontinuous. Alright, so the word state simply implies that we only have to look at the diagram. We don't have to do any working out. Okay, and we can see that the graph is discontinuous at those 2 points. That's where there are holes in the graph. Now, when they're talking about continuity, remember we're looking left to right. So this gap that is there between the functions that I've highlighted in yellow, that does not have anything to do with the discontinuity of the function in terms of the x values. Right, so we would now simply say that the function is discontinuous at those particular x values. Right, so x equals positive or -1, the function is discontinuous, and in fact it's continuous for all other x values, and that's indicated by the arrows that show that the function is going to carry on forever. Okay, the second part of the question says establish the type of discontinuity at each value. So this is when you've got to do your limits, etc. Okay, but let's look at them separately. You can see that there's a jump discontinuity at x equals -1 because there's a gap between the function at the 2 parts of the composite function at x equals -1. So we're going to prove that, okay? So there's a jump discontinuity at x equals -1. And we've got to show why. We can't just state that. All right, so we're going to look at the limit as x approaches -1 from the left-hand side, and in this case the function is x plus 3 on the left-hand side, right? And that equals -1 plus 3, which is positive 2. Then we're going to look at the limit as x approaches -1 from the positive side, and in this case the function is the absolute value of x, which means that it's just simply -1 in the absolute, which is equal to 1. Okay, so therefore the limit as x approaches -1 does not exist. Okay, the limit of f of x does not exist, and that is the proof of why it's a jump discontinuity. Right, secondly, we're going to discuss this type of discontinuity, and I'm sure you can see from the diagram it must be a removable discontinuity because the limit clearly exists from the left and the right, but we've got to show that proof. Okay, so we will say that there's a removable discontinuity at x equals 1, and we're going to prove it with limits. So we're going to say that the limit as x approaches 1 from the negative side, we can see from the diagram as x is approaching 1 from the negative side, the y value is 1, or the limit is 1. Okay, so the limit of f of x, and in this case, when we're approaching from the left-hand side, it's the absolute value. So substitute 1 into the absolute value, and we get 1. Right, the limit as x approaches 1 from the positive side is now the function 1. So obviously we can't substitute 1, so the limit is 1. So because the limit exists, we would say therefore there's a removable discontinuity at x equals 1. So therefore the limit as x approaches 1 of f of x exists at x at 1. The third part of the question asks you to redefine the function so that it is continuous at x equals 1. Okay, so if we go back to the graph, to make it continuous at x equals 1, we would have to include that point. That's the only way it would be continuous. Remember, the limit from the left and the right both equal positive 1, but for it to be continuous, then it needs to be defined at x equals 1 as well, so as I've highlighted with the pink dot. Okay, so going back to this, we basically have to rewrite this. Now, there are two ways you could do it. You could either write it like this. The first part will stay the same. Remember, we're only interested at x equals positive 1. So x is less than or equal to -1. The absolute of x if -1 is less than x, which is less than 1. And lastly, 1 if x is, and here's where we change, instead of just greater than 1, it's going to be greater than or equal to 1. Right, that's the one option. The other option is to include the 1 there, but not include it in the second part. So both of these two options, that one there and that one there, would make the function continuous at x equals 1. You don't have to give both, you just have to give one of them. Right, example 7. Discuss the continuity of g. G of x is given as 2x minus 4 if x is less than 2. G of x equals 2 if x equals 2. And g of x equals x squared minus 4 if x is greater than 2. I'm not going to sketch a graph at this point because I feel it's important that you're able to do this directly from the algebra if a graph isn't given. But essentially, we're looking at these points, okay? And those points are where there might be possible continuity or discontinuity issues. All right, so we need to investigate what happens to the left of 2 and what happens to the right of 2. So the limit as x approaches 2 from the left-hand side, and remember the function now is 2x minus 4 because that's the function that's to the left of x equals 2. We can substitute straight away and we get a limit of 0. Right, then we look now at the limit as x approaches 2 from the positive side, and the positive side is x squared minus 4. All right, because again the parabola, the x squared minus 4, is to the right of x equals 2. And again we can substitute straight away, so it'll be 2 squared minus 4, which is also 0. So from that, we can then conclude, therefore, the limit of g of x as x approaches 2 is equal to 0. So at this point, because the limit exists, that could imply either that the function's continuous at that point, or it implies that there is a removable discontinuity. So we have to see which of the two it is. So the deciding factor is that we can now say, hang on, but g of 2 equals 2. And that is given to us by this portion of the composite function. So that then means because the values of the limit do not equal when g is equal to 2, we can conclude that there is a removable discontinuity at x equals 2. Okay, and that last sentence is important for you to give as a conclusion. Okay, so there's a removable discontinuity at x equals 2. Now, it's also important to add something here because of the nature of the question. They didn't just say discuss the continuity at x equals 2. They said discuss the continuity of the whole graph of g. So because there were no other points here other than x equals 2 we had to worry about, we can also now conclude that g is continuous for all other values of x. Example 8. You're given that f of x is equal to x minus 3 if x is less than or equal to negative 1. F of x equals ax minus b if x is between negative 1 and positive 1. And f of x is equal to 2x plus 5 if x is greater than 1. Alright, so here they've told you the whole function's continuous. So there's no removable or jump discontinuities. So the moment they tell you that it's continuous, then that first definition applies, where the limit is equal from the left and the right, as well as equal to f of that x value at that particular point. Right, so the best way to do this is to draw a kind of a graph, a diagram at least. Okay, so we're going to split this function into 3 portions. All right, and the changeover portions are our critical values at this point. All right, so we have negative 1 and we have positive 1. To the left of negative 1 is x minus 3. In between negative 1 and 1 is ax minus b, and after ax minus b is 2x plus 5. Right, so what we're going to do is we're going to see what is the limit as x approaches negative 1 from the left-hand side. Remember, because we're to the left of negative 1, and the function is x minus 3. Right, so that gives us negative 1 minus 3, which is negative 4. Right, then ax minus b. Now, we're going to say what is the limit as x approaches negative 1, this time from the positive side, because ax minus b is on the positive side of the function of x equals negative 1. Right, substitute in, we end up with a times negative 1 minus b, which is negative a minus b. Right, then I'm going to squash this in with another color here. We're going to now look, because remember we're dealing with this 1 now. So the limit as x approaches 1 from the negative side, because ax minus b is to the left of positive 1, and the function again is ax minus b. So we can substitute in, so we're going to have that equals a times 1 minus b, which is a minus b. Right, and then lastly, we're going to look at the 2x plus 5. So now we're looking at the limit as x approaches 1 from the positive side, because 2x plus 5 is on the positive side of x equals 1. And we substitute. So 2 times 1 plus 5 gives us 7. Okay, so the key parts of this working out that we're using are the final limits, right, of each of the 4 pieces that we worked. Remember, there are 4 because we've got minus 1 and we've got 1. So we had the limit approaching negative 1 from the left and from the right. and then we had the limit approaching positive 1 from the left and positive 1 from the right. And remember, because they told us that the function is continuous, then that means that the limit of x approaching negative 1 from the left, x minus 3, excuse my dog walking, I hope that didn't disturb you, must be equal to the limit as x approaches negative 1 from the positive side, and in this case, it's ax minus b. All right, now we've already got those values. Minus 4 is the limit, which equals minus a minus b. All right, and there is equation 1. You can make that a bit simpler by dividing by a negative if you want. So 4 equals a plus b, and let's call that equation 1. Right, then, on the right-hand side, we've got the same thing. The limit as x approaches 1 from the negative side of ax minus b must be equal to the limit as x approaches 1 from the positive side, this time 2x plus 5. Why must these limits be equal? Because they've told us that the graph is continuous at that point, and because it's continuous, we can work out a and b from that. So we've already worked out these limits. The limit as x approaches 1 from the negative side is a minus b, and the limit as x approaches 1 from the positive side is equal to 7. All right, so we can now solve simultaneously. You can solve in any way that you want. I'm going to say let a equal 7 minus b, and that 7 plus b, that's equation 2. So I'm going to now substitute equation 2 into equation 1 so that I get 4 equals 7 plus b, so therefore 4 minus 7 is negative 3, 2b, and therefore b is equal to minus 3 over 2. We can then work out a fairly easily. I'm just going to go into that equation. So if b is negative 3 over 2, then a equals 7 plus negative 3 over 2. So that's 7 minus 1.5. So that's equal to 5.5. All right, so 5.5 is also 11 over 2. All right, they just asked for the values of a and b, so you can leave your final answer at that.